Hello, testing. All right, good morning to everyone. Today we have our replacement class. How's your weekend? Refreshing or study? Haven't wake up yet, Haven't wake up? Yeah. Okay, let's not wait for the rest. We just since we have recording also. Before we start, quickly recall a few definition we did last time. So in particular, what is a subgroup? Let's recall what is a subgroup. Subgroup is. So when you talk about subgroup, right? Okay, so there's a word group there. So you need to start with a group first. Okay, so let's start with a group. So let G be a group. You still remember what the group is? What's a group? Set or function? Set. Set with what? Three things, right? What are the three things? Associative LC, and then identity element exists, and then inverses exist for all elements. Okay. So what's a subgroup? So a subgroup, say H of G, is a, first of all, subset, right? Subset of G that also satisfy three properties here. Okay. Also three properties here. Anyone can recall what are the three properties? Also need an identity. Okay, identity exists. What else? Inverse also exists for all element in H. Good. This for all H in H. And also lastly, you need to close. Okay, so close means what? If you take two elements in H, okay, you multiply, for sure it is in G, right? Because it's an LLC. Okay, but you require it to be in H as well. Okay, stay in H. Okay, stay inside a subspace. Sorry, subgroup. Subgroup. All right. So there's an example, few example I gave in the lecture. So a bit of apologies last week. So I keep updating my notes. Lecture 4 and lecture 5. I keep updating because there are little typo, there are small typo on these indexes. We try to make these indexes consistent. I guess I think today's morning one is the most outdated. So you can download the latest one. And also we have the type version up already also. Okay. Yeah. Thanks for the team to work it out. And what? And yeah, so I want to return to this examples of subgroup here, in particular on this complex number and the root of unity. Okay. So last time I talked about this root of unity. So what is the root of unity? They are the roots of the polynomial equation to x to the power n equals to 1. Okay, so what does this mean here? X to the power n equals to 1. If you take the modulus of this x, right, it should be length 1. Okay, so these are the knowledge from complex number. So also our team, right, try to write out preliminary knowledge to AA1. For example, what did we use? We use natural number, uh, a real number, right? And then matrices, and then for now complex number. So all these preliminary knowledge that you get from previous courses, we try to compile them into a document also. And then if it's done, hopefully 2 more weeks. That's it. Okay. They say 2 more weeks. Hopefully, then we will release it. So you can help you to recall whatever previous knowledge that's needed for this course. Okay. Right. So speaking about this root of unity here, so you can see that what did you see? So this root of unity, you can write out the form of what is called the name of this complex form. What's the name? In of argument. Radius and argument, correct or not? Radius times e to the some x, some multiple of 2 pi I, correct or not? Sorry? Argons, right, argons, right. Argons, why is it argons, you know? Argons, argument. Okay, the theta is what we call the argument. Okay, and then r is the radius. Okay, argument. So because you learn calculus 2, right? So in 2R2 space, right? What is the other convenient coordinate? Polar coordinate, right? So polar coordinate controlled by 2 variables, which is radius and angle. So this is how we describe the complex number. So the radius here, you can see that all of them with coefficient 1. So their radius is 1. Okay, so the only changing is the angle, and 2 pi times the multiple. So you can see that they only make up to the rational points of the unit circle. Okay, then Eric pointing up. But what I want to say is there's still unit circle line between them. Okay, there's still unit circle line between them. Okay, so unit circle also form a subgroup here. Okay, so this unit circle here is defined by all the e to the 2 pi I x for all x in. Okay, in fact, we can fill it up. This is how you parameterize your circle in calculus 2. But in this case here, we do in a complex plane, so there's an I there. But in general, you just take e to the 2 pi x in R. Okay, this is your parameterized curve. Okay, in calculus 2. Later, we will see fun stuff with this circle here. Okay, soon we will see how we gonna play with it. Right, so all these actually not just subgroup, right? You can see that they are all proper subgroup. Okay, proper subgroup. Not just subgroup, but proper subgroup. Because they are proper subset. Okay, any questions so far? Any questions so far? So there's one more thing I want to recall before we start new stuff today. There's one very important concept in group theory, which is called the generating element. Okay, so this generating element is very important. So let's record this notation here. Okay, so I go back and check already. This is called an angle bracket. Okay, please remember angle bracket, slight angle. So this angle bracket with some group element here, what does it mean? Okay, so we define as this is the smallest, okay, smallest subgroup, okay, of G generated by A1, A2, and AN. So these elements are in G. Okay, so it is valid to ask what does it mean by smaller subgroup generated by these elements. Okay, so it follows that, okay, we will keep continuing with this definition. So you need to require that elements, sorry, identity elements is inside this subgroup here, okay? And what else do you need to do, okay, to be a subgroup? Three things, right? Closure, identity, and inverses. But here, identity, I already put it in, okay? Must put it in. Even though, so I make a comment here, even though all these elements are not identity, okay, I still put it in. So by default, if I put angle bracket of something, identity element is already in there. Does it make sense? Okay, by default, by default, even though, or even true, even though. Okay, so two more things we need to satisfy. So it has to be closed under LOC, okay, and it has to be closed under taking inverses. Do you understand what does it mean by close under LOC and inverses? Do you understand what does this mean? Term B is term B here now. Yeah, do you know what does it mean by close under LOC and taking inverses? Let's say talk about close under LOC. What does it mean? Can you speak louder? Louder a bit. What do you mean by 循环 recycle? Recycle? What is recycle mean? Close. Not quite. What is recycle? Change another one. Hurry. Hurry. Okay, hurry. What does it mean by close under LOC? What do you think? You don't know. Okay. Sing any Sing here? Not? Yeah. Sing no. 小月. You know what's close under LOC mean? Okay. Yeah, good. So if you take two elements and then you do LOC together, then it will stay inside the group. Okay. So all the composition happen within A1, A2 until AN will stay inside this set here. So close under inverses means what? If you take inverses of this guy, it will still stay inside. So you need to do repeated step, correct or not? If you take composers, for example, A1, A2, does the inverses of A1, A2 have to be inside the set or not? Yes, because you need to close under inverses again. Okay, so you take inverses and then do LOC, then do inverses, LOC. You keep doing. It will stop, right? Will it stop or not, this process? Do you generate infinitely many elements? This process seems infinite, but do you always generate infinite element or not? Why not? Because what? Maybe the set you started with is not infinite. For example, what I give you that example, right? So if you look at the set generated by 2 and 4 inside where? Z6. So this is the smallest subgroup in Z6. But what is all of the element here? You still remember? What are all the elements here? Huh? Which is 0, 2, and 4. Just 3 of these only. Correct or not? Think about it. Calculate, do the process. What are the inverses of these elements? 0 is 0. Okay, 0 inverse is 0. 2 inverse is what? 4. 4 inverse is what? 2. So it cycles back. And then what are their composition? 2 plus 0, 2. 2 inside here. 4 plus 0, 4 inside here. 4 plus 2, 6. 6 is 0, 0 inside here. So this process might stop if your set is finite. is your group is finite. Okay, if your group is finite. Okay, does it make sense? So please remember these examples. Okay, examples is really important. Okay, to help you understand the concept. Okay. Any question? Question or not? Question? Question? No question, Ling? No? Okay. Feel free to ask. Feel free to ask. Don't be shy. Okay. So speaking about these generators, right? Do you recall any similar things you see before no? About these generators? So what's the idea about generators? You use a few elements to build out a set or build out a group or a subgroup. Okay. So you should have seen this in your linear algebra also, right? Where what? You can build your vector space just using some basis, right or not? So people tend to confuse with these two words, generators and basis. Okay. So generators, usually we will use it for a set with LOC. Okay, we know how to compose. So generated here means you need a LOC to start with first. Okay. And you need to build something. How you build? Of course, you need to put things together. But what does it mean by put things together? You need to have LOC. A law of composition. You need to build things. But basis usually we only keep it for vector spaces or any abstract vector spaces. Okay, not just Rn. Any abstract vector spaces. Okay, and then what's the difference? Okay, how they build the spaces. Okay, how they build their spaces. So in generators, what do you do? What does it mean by generate the group? So wait. So let's call these element as generators. Generating elements, we call it generators. But you can listen first. Now I just trying to give you some idea because later we'll come back to the generating ideas again. So what does generators do? So every element, okay, let's call our set S. In our set S, the set S with LLC, okay, can be obtained, okay, can be obtained by composing the generators, okay, the generators in S, okay. Let me give you the example. Can you guess what's the generator of Z? You find a generator of Z. Okay, maybe I need to tell you the composition also. Let's say addition. Yeah, anything can generate the whole Z or not? Just by close under LOC and then taking inverses and then identity has to be in there. Can you find some generator here? Huh? N plus 1? N plus 1, what do you mean by N plus 1? What's the N? Can you pick an N? Z, right? You can talk about element here, right? 1, 2, 3, 4, 5, 6, -1, -2. Anyone can generate this set or not? Yeah? Any guess? Guess a number. Okay, guess a number first. Huh? You say 1. Okay, you say 1, right? So let's see what happens if I have 1 inside this angle bracket here. Okay, first of all, what do we require for this smaller subgroup to be? You need to have 0. Okay, 0 and 1 is inside here already. And then what else you need to do? Closure, 1 plus 0, oh sorry, 1 plus 0 is what? 1, no? Then what else you need to do? 1 plus 1, no? 1 plus 1 is what? 2, no? 2 plus 1, 3, no? So meaning what? From 1 here, you can generate what? The whole natural number already. What else you left with in integer? Inverses, but what does smaller subgroup mean? We need to add all the inverses in. So yeah, yes, sure, yeah. Because we just generate our Z, the internal group using one element here. Yeah, no? Does it make sense? Okay. Any question? Okay. So how about basis here? Okay. Basis here is similar, but remember, what's the LOC we have in vector space? So the LOC we talk about here is called the what? Linear combination. Okay, so in the basis case, we have all the element in our vector space can be written as a linear combination. Okay, written as a linear combination. Can anyone recall what a linear combination is? Linear combination. It's basically two things, right? Two things. Okay. One is the scalar multiplication. Scalar multiplication. And the other is the vector addition. Okay, two things. Correct or not? So how do you write these? Let's recall the notation for you. So we'll write that R2, for example, is the span of E1 and E2. So what does the span of E1 and E2 means? So there is a definition for this span here. So this is really just defined as a linear combination of the all things inside the bracket, which we call the basis. Such that what? Such where this AB lies, this really depend on your scalar field here. So linear combination. So where is the scalar multiplication? So scalar multiplication happens in each terms here. Okay, so let's call it S, this one. And then the bottom one, let's call it A, addition. Okay, so you have scalar multiplication and you also have vector addition. Does it make sense? Okay, so let me test you. Whether scalar multiplication or vector addition is a LOC or not? Or are they both LOC? Which one is LOC? Sorry? Multiplication, scalar multiplication, addition. Vector addition is a LOC. Why? What does the vector addition do? It takes two vectors and then give you back another vector. Correct? Not x cross x to x. Okay, take two things in the element, give you a vector. Okay, but what does S really do? You need to be very careful here. What scalar means? What does scalar means? Scalar means what? Sorry, real number. Not quite. We can change scalar. Do you know? In more general maths, we can change scalar to complex number, real number, integer, anything. Okay. But our vector space is the same. Okay, so meaning what? We have a, let's call it a scalar field now. Okay, scalar field time vector, you get another vector. For example, what? You take a number here, okay, you multiply by a vector, and then you get another vector. So scalar, in general, might not be the vector space you look at. Okay, in general, it's not. In general, it's not. Okay, in general, it's not. For example, in this case here, you see, your scalar stay in R, but your vector space is R squared. Okay, one dimensional more. Okay, okay or not? Can you see the difference or not between scalar field and vector space? Does it make sense? So there are two operations on vector space actually. Okay, and then only one of them is a LOC. Okay, vector addition is this one is a LOC. Let me write it down. So this is is LOC. S is not LOC. Okay. Okay. So another thing I want to point out is the nature how they built, the nature of how they build your space. Okay. So for generators, we just know one LOC. But for basis, what do you know? You need to know two things: scalar multiplication and vector addition. Okay, you need to use these two operations to build your space. Right, correct or not? See what's the element inside your vector space. Linear combination. Okay, whenever you see linear, this word, linear, then it means two things. Scalar multiplication work and vector addition work. Okay, these two things. Whenever you see linear. So in linear algebra, there's only really these two operations you can do. That's why it calls a linear algebra. Okay or not? Linear. Scalar multiplication and vector addition. These two things. That's all. Okay, about linear algebra. So any questions so far? If you still tricky about this generators here, we will revisit again soon, very soon. Either later or tonight. Okay, any questions so far? Or do you have any question on lecture notes or not? There's a lot of typo, so I have updated. So please download the latest one. And if you found out the type 1 and the written one is not in sync, it's different, please contact me or contact, where's the rest? Hey, who helped me to type the lecture note? Can you raise up your hand? Ziming, can you raise higher? Raise higher. Shu Yao, can you raise higher for the rest to see? Then they can find you. So we have Eric here, and then Ziming at the back, and then Shu Yao here in the black jacket. So if you have any problem with the typeset lecture note, if it's different from my written one, you can talk to them. Okay, and then or if you suggest we want to add something in, you can talk to them or talk to me also. Okay, for example, you think that this concept he said right not clear one. I think need to add something in here. And then you can suggest them or suggest me. Okay or not? Does it make sense? Okay or not? Hello, hello. Can you guys understand? Understand or not? Okay. And then right. So please continue to do arting tutorial question. Okay. If you do more than what I requested, right, the extra question inside arting, right, you can check answer solution with me. Okay. Kam Ping is also doing it, so you can form a team with him also. Okay, you can do it together with Kam Ping. Does everyone know who is Kam Ping or not? Kam Ping, can you raise your hand? So he has a long hair, easy to recognize. Yeah. Yeah, you can discuss with him also. Okay. And then what else? Okay, the other thing is if you make difficulty in lectures, so please go to office hour because you cannot expect me to teach you hand by hand in the lecture. Okay, this is not how lecture works. So if you need to teach hand by hand, you need to go office hour. Okay, this is what office hour for. Okay, you need to go there. And I already recruit all the top students in my office hour, you know. All the person you see, they are top students in different batches, starting from 2204, 2209, 2304. All the senior top guy is in that meeting room, you know. So make sure you make full use of them. And you also can ask them about their life experience, study experience too. Okay. Yeah, you can ask them. Okay. Does it make sense? So please come get help. Okay, get help. Right. So let's start a new content today. So today we'll talk about important concept about cyclic group, or rather cyclic subgroup. And cyclic subgroup. So what does cyclic mean to you? Bicycle, good. What's the idea of bicycle? Why is there a bicycle? Why not tricycle? Got tricycle, right? Tricycle means what? 三轮车 good, very good. So there are two 轮，两个轮 okay. Two, what do you call that? 轮 wheel. Thank you. I almost said roda. Malay roda. Okay. Two wheels. So what happened to wheels? What is wheels? Cycle. Okay, you come back and forth, come back and forth, come back and forth. Okay, let's see how the cycles concept get into this subgroup here. So let's give you a statement. Okay, I don't want to say theorem, a bit big. This is a statement. What's the statement here? If you have G be a group and let any element in G, okay, then what can you consider? You can keep taking power of this element here. Okay, how many power you need to take? Set many power. Okay, meaning what? What can you do here? What's the element inside this set? Okay, if you don't understand the set, right, you should list down the elements inside here. What's the element inside here could be? S to the what? 0, x to the 1, no, x to the 2, no, x to the 3, no, x to the -1. Okay, z many of them. Okay, I don't care what is x, but there are z many of them. And then we claim, so this is the first thing we claim. So this is a subgroup G. Okay, so this is the first thing we claim. We start with a set and then we tell you that this is a subgroup. And then the second thing is, moreover, this is actually the smallest subgroup of G that contains X. Okay, so this is a smaller subgroup that contains X. Okay. So what does it mean by smallest here? Can you imagine? Can you elaborate more? What does it mean by smallest subgroup that contains X? What can you imagine here? Okay. So if you cannot imagine subgroup, right, you just imagine subspace of subspace. What does it mean by this is the smallest classroom that include you? What does it mean by this is the smallest room that include you? It's a toilet. So you like to spend your time inside the toilet. Okay, so what does it mean? This is the smallest room that can include you, meaning you can be in a different room also, right? Okay, you can be in a different room also. Maybe the other room is larger than this room. Okay. So what does it mean by smaller subgroup here? It means that that is, wait, let me see. That is every other subgroup that contains you must also contain the whole set H. Okay. Okay, so draw it out. So in my max, you can draw it out. So you have an X, right? So you have an X. So let's start from a G. Okay, sure. Let's draw it. So let's start from a G. Okay, you take an element X. Okay, too close. So I'll do like this X. Okay, and then you can do X0. So X equals to X1 by definition, and then X2, and then X minus, like that. Okay, no, X minus 2, and so on. Okay, and then you consider this as a H. And then what does it mean by the smallest one? If there's any other subgroup, so let's name these. G is a group, so it's a group G. So here group, and then H is a subgroup. Okay, if there's another subgroup contain X, meaning what? So if there's a subgroup that contains H, meaning what? So let's say this blue one is the smallest one. Okay, so what does this H prime have to be? It has to contain H. So meaning what? You really need to Wait, make this H bigger. So how to make this bigger? This into. Hey, why now so restrictive on this? No, here. So really, you need to contain the smallest subgroup here. Okay or not? Okay. Does it make sense? So it's the smallest one. Okay, so it must contain in all the other subgroup that contain what? Contain the X here. So let's label it. Sorry, label the wrong guy, this guy. Okay. Okay, understand? Okay, so we need to prove these two claims here. So there are two claims inside this statement here. So there are two claims here. Okay. Right. Should we do it or you want to try first? How about I let you try first? I can let you try about 2 minutes. Okay, you can discuss with your friend. So you need to check subgroup properties. So how to check? I think I need to tell you the LOC first, right? So what's this LOC? So in particular, what is this x to the power n? So this is exactly what you see in your assignment. Okay, so what do you see in your assignment? So let's keep the notation here. So this Sn is defined as what? S dot 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 dot. How many time? N time. Good. So this is exactly this. Yeah. Okay, let you try first. 2 minutes. Check 3 definition of subgroup. Try write down. Yeah, try write down. Write down what you need first, and then think about how you're going to. Okay. Any idea? So where should we start? You need to tell me where we start. You will get stuck for sure. Okay, I want you to learn how to get unstuck in my class. Okay, because this problem of unstucking, right, is very important in your life. In particular, for us, one is research. Okay, the process to get unstuck is very important. So you need to learn to get unstuck. Okay, if you never get stuck, you are a baby. You're seriously a baby. Okay, you need to always get stuck and unstuck. This is a difference between adult and baby. Okay, no. If you are an adult, you need to learn how to get unstuck. Right. So let's prove it. So first thing we want to prove what? Like what I said. I think it's very good. You guys really got listen to what I say. Put down what you want to prove first. Okay, this will tell you how to go forward. Okay, so what's the thing we want to prove first thing? Want to prove that hash is a subgroup first. Okay, let's prove hash is a subgroup first. So what do you need to show for subgroup? 3 things, list it out. Closure, and then identity, and then Inverse. Good. So this is what we discussed in the start of the class. So closure means what? Take any two elements, multiply together. Okay, still inside the group. So take any A, B in H. But do you know more about A and B or not? You know more about A and B? Okay, let's bring down the definition of H. You know more about A and B or not? Yeah, good. So let me put here. So what you know about any two elements inside here is x2 something. The thing is integer. Okay, so you can write out the form of this AB. So take any A and B in H, then there exists some, let's say, Mn in Z, such that A equals to x to the M, and then what? And then B equals to x to the N. Understand? Okay, huh? But I think there's one thing I didn't tell you. How about what is S negative 2? Punching us, what's S to the negative 2? Did you ask? Did you ask? 我听到你心里的声音了，你问吗 ？S 的减2是什么？有吗？有问吗？有哈，有哈，很重要，我也没有告诉你，所以你要问。So what is S to the negative 2 actually? Can you imagine? How do we define? Okay, inverse is later we'll disclose why is it an inverse, but how does it define? Let's say x to the okay, so how do we do this? Let's do it more formally. Consider m, let's use another notation, p greater than 0. So how do we define x to the minus p? How do we define this? Sorry? 1 over. Okay, so in our case, in extra algebra, we don't like 1 over. What do we like? Inverse, taking the power of -1. Okay, so this is defined as taking x to the -1, multiply x to the -1, multiply x to the -1 until how many times? P times. Okay, so this, I think this we already defined everything. Okay, so in this case here, what happened? What happened? What happened? What happened? What happened here? So in this case here, is it better we do inverse first? I think it's better we do inverse first. I need to tell you what does this inverse do. Correct or not? We do inverse first. Let's do inverse first. Let's do inverse first. I think it's more natural to do this inverse first. So if we do this inverse, what do we do? Again, take any A in H. We want to show that A inverse is in H also. Okay, but since A is in H, what happened? There exists an M such that A equals to x to the M. So what's this M here? M live in where? In Z. Okay. So do you know what's the inverse of this x to the M or not? Then who is the inverse of x to the M? The inverse, A inverse of A is simply what? S to the minus M. How do you check it? How do you check it? We do it in your assignment, right? What do you need to check? That is S to the minus M to x to the M is identity. And also, you need to check two things. Some of you in your assignment just check two things, one thing. So tonight we will discuss your assignment. Okay, tonight we'll discuss your assignment. So x to the minus m times xm equals to identity, and the other thing is xm times x to the minus m is identity. Okay, but is it identity or not? Is it identity? Identity, right? You can use associativity to cancel out. Correct or not? Starting from the middle. You understand what I say? So let's do some little working here. So little working, let's do a small example for you. Let's example take m equals to 3. Then you need to imagine for general m what happens. So if m equals to 3, what happens? X to the minus 3 times x to the 3. But what's the definition of these two? So you have x inverse times how many times? 3 times, and then multiply by x times how many times? Also 3 times. Okay, good. But you see, they are not in the same circle yet, not in the same grouping yet. So they cannot cancel. So what do we need to do? We use associative, okay, because we live in a group. So we can associate, okay, such that the middle two meet first. You know, we can associate until the middle two meet first. And then we can use the property of inverse. Okay, S inverse is the inverse of x. Okay, so we'll say that this is equals to the identity. Okay, since what? Since since that x inverse is by definition, okay, by definition the inverse of x. Okay, so you can imagine that we can keep cancelling, right, until you cancel all the x's. So you keep going, okay, keep going, keep associate. Can follow? Okay, can follow. So you need to try and fill out the space. Don't write these in your assignment. I'm just trying to explain what happened. You need to write them out, okay? Write them in. Okay, good. So let's come back to closure here. What happened to closure? Obviously, you need to consider A times B here, which is what? XM times XN here. Meaning what? If you look closely what happened at the cancellation here, seriously, you just do indexes addition. Okay? It's really the indexes you learn in your high school. Okay? If you go and split it up like this. Okay, it's really just addition. But this means what? This is in H because what? Because m plus n should be in Z. Okay, close under addition. Z is close under addition. Now the question here, what's the identity then? Who should be the identity if you look at the power addition? It should be x to the 0. Why? You need to show. So the identity is x to the 0. Why? You need to show. Go back to your definition. That is what? That is x to the 0 times all the other element xm equals to the element xm. Another direction you also need to check, right? Left and right. Okay. Sm dot x0. This has to be true for all the elements. Is it true or not? True, right? Because what? If you consider x0 times xm, what is this by definition? This is x times how many xm? M times. But here is 0 times. Okay. So you're still left with m times. Okay. So a more convenient way, actually we need to make a notation here. Seriously, how do we call this n0 previously? We called it E. That's why in your high school, you write x to the 0 is equals to 1, right? Yeah. Doesn't it feel weird last time? Don't feel weird. y2 to the 0, 2不减7就变1了。老师讲的嘛，是不是？那也可以，不可以？不可以都是老师讲，OK? So now you are learning mathematics now. So you need to ask why. Okay, your high school teacher teach you like this. And sometimes, or a lot of time actually, they will give you a wrong concept. Okay, so you need to change it when you learn proof now. Because now we are proving to you. Okay, we prove to you something is wrong or correct. Yeah, you need to be ready to change your whole mindset and accept new stuff because this is true logic. Okay. Right. So this notation is very important, so that it won't confuse you about S0, S1. Okay. So I want to remind you that S to 0 is not equal to x1. So you can imagine S0 is like empty, empty string, empty x. Okay. We just put it as identity. Okay, very important. This is x to 0. Right, before we take a break, let's prove the last statement here. So we need to show that show that hash is the smallest one. Okay, smallest of G containing X. So this containing X is very important here. So how to show this? Just now we said that if any other subgroup G subgroup, let's call it hash prime, then hash prime has to contain OH. Okay. So let's suppose hash prime is another subgroup containing X. So we need to make our proof into some statement that we can verify. So what do we need to verify actually? We need to make it into a mathematical statement. So what do we need to do? It boils down to show that H is a subset or a subgroup of K. Okay, it boils down to this. Is it a subset or not? What do you think? Sorry, not K, H prime. What do you think? H prime is what? By definition, is a subgroup again. Okay. If H prime contains X, what else does H prime have to contain? H prime is a subgroup of. Subgroup have how many properties? 3 properties. And then this subgroup contains X. What does this 3 property has to do with this element here? X plus S is in there. X composed with X is in there. Closure. And then the inverse of X. And what else? Identity. But if you put everything, these things in there, isn't it just the H we started with? Okay, so what we will say is this H prime here, since by assumption H prime, since H prime is a subgroup containing X, so it has to contain all products. Okay, the law of composition, any composition of X and X inverse. Okay, you can take inverses. And then you can take combination between inverses and product of X. But all these are just our H that we define. Hence, hash is in, is a subgroup, smaller subgroup inside hash. Okay, does it make sense? Not that we don't claim proper here. We don't claim a proper here. Who knows? There's some space that there's only one subgroup that contains X. And maybe there's only one subgroup in that group. And so we don't claim proper here. Does it make sense? Okay, I'll give you an example first before we finish up. So let's say, can you get a cyclic subgroup from Z or not? What kind of cyclic subgroup you can get? Just now I tell you one, right? You can get the smallest group generated by 1. You use 1, no? 1 plus 1 plus 1 plus 1 plus 1 plus 1, and then take the inverse of 1, minus 1, minus 1, minus 1. Okay, so in this case here, you see, if there's another subgroup that contains 1, then it has to be the whole group. They can be equal. Okay or not? But can you find a proper subgroup in Z? Proper subgroup in Z. Can you find a proper cyclic subgroup? Proper one. Proper one. Can you find or not? Say again. 1, 2. What do you mean by 1, 2? 12. 1, 2 is what? 1 and 2. 1 and 2. No, we want to talk about cyclic subgroup. So we just start with one element. We just start with one element here. Pick any one. Okay, which one you can pick? Wait, 0 last time we talked about, right? It's a trivial subgroup. It's in every group. We don't typically talk about this guy. Sometimes quite trivial. Any non-trivial one? 2. So what does what's the hash generated by this 2? Inside here contains what? 0, 2, 4, 6, 8, and then take it the inverses, you have what? Minus 2, minus 4, and so on. Okay, no? So this is a proper one. No, no. 2. Taking composite for 2 plus 2 plus 2 plus 2. And then close under inverses. So you have a negative. Negative of this. Understand? You must understand this notation. This notation is really, really important. And this notation. Very, very, very important. Generated. Any question before we break? Question? Please ask, Please ask question. No question. Let's break until 10:07. Okay, so I will take attendance. Xiaoyang is Pan Xiaoyang here now. Hong Jie here now. Ziming got. Zihan. Zhen Zihan. Okay. Adrian got. Jia Ling. OK。子轩这边是 OK。谁是子轩？哎 ，OK。Lydia 个嘉玲，所以是嘉玲。OK， 哪一个是嘉玲？2个。OK， 邵琪，OK，Eugene here了，还没有来。OK，Jasmine，OK，so Jasmine，Albert， 那个陈碧个金鱼，浩瑞 ，Yes， 子豪，戴一成， 心仪的什么？修同的修同，yeah. 冰夏，冰夏，Where's 冰夏？Not here. 小圆，小月，sorry，小月，子航，刘子航，OK，冯瑞，Very good，宇轩，Yes，嘉怡，方瑜，OK，哎，just now is 嘉怡，right？嘉怡，方瑜有嘉怡，哦，方瑜嘉怡，OK，good，舒瑶，云溪，I think 是一个苍月，谢苍云，苍云，严胜，Yes，Eric God，一凡，Yeah，钟一凡呢？钟一凡，Not here。安平 God，若轩，若轩，若轩，哎，sorry，哦，sorry，忘记了。赵胜，赵胜，Manchun God，OK，傲天 God，金星呢？OK，金星，一航是一航吗？也是一航，不要站，一航，OK，另一航啊，不是，OK，修着，OK，Risha，这个庞星 God，林恩 God，伊恩呢？伊恩，OK，正月，OK，正月，赵瑞，absent，where is he？Hostel，sick 啊，sleep，OK，金鹏，米泽，哎，什么？怎么来的？把他的那个 N 和 R 绑上了啊，知道 N R 对，
这个我已经全部打过了那个。
我会抄你，放心。
好，我觉得
我就是用那个地方应该放不了多少资料，是因为我跟说资料就是看一次。
我看一下，哎，我觉得 N 的这些东西都可以加进去，因为蛮重要。可是 R 的东西就
我已经打了，你不要告诉我不用。
放进去吧。他打了多少？我好像没有把全部放进去。我没有把全部放进去，就觉得这些蛮重要的，因为觉得这个蛮重要的。但是如果是那种 upper bound，那个 as definition 就好一些，
就这样了
啊，那种普通的加进去，因为他们会看到为什么。
这个不要了
这个不要，这个
打了什么？你要
因为你要介绍 definition，所以你就 definition 嘛。但是这个不要了，这个不要，这些不要讲。就 definition，就是 real number 那些 definition 要用到的 definition 全部进。然后就号码做的 operation 加到这个一大于零的一大加一个，做到这个很好，因为这是号码的一些事情。但是 real number 那种 upper bound 那种 proof 不要讲，那个是 M。
对，一样。
definition 要，因为你要介绍为什么，这个才，因为你看到为什么你，但是那种很多可能也可以就是加的比它也就可以用这些然后这个要这个 result 要这个 result 要弄好，然后就告诉人家只有一种原理，好，而且没有不会动的，但是你去读都多，你要不要读？这个蛮重要的，全世界只有一个人能做的。 你换符号，它也是那一个了。MAT211就是里面的一些那些 real number 能够做的事情，就有另外一个 real number，就是那种
我刚想过去跟你说，我当时我发现是没有放掉一个
但是就很烦。
那你给我解释一下那个三角形什么意思？我没看懂。
哎，我也不懂，我也没有想要人看懂，我只想让起来。
那你放上去干嘛？
就觉得就拿来摆美吧。我其实没有想不开。
我不知道，我就放那个。
你也放那个三角形，
都放啊，
让人家去想。因为我没有想，
你都没想。
你看那个 Otonian 拿挂号的，不问号，放问号的，不要比翻给他们啊。
哪个是那个？
再来个。
好，我们俩
讲那个旁边。不在这里。
你在我刚刚看到了。在这里吗？
他这个就是我会看啊，
然后这个图，
好像是
说明你这是什么鬼东西？
就这个乘这个等这个，对吧？这个乘这个等这个。
哦，这个乘点等这个数字。
哦。
这个也可以等。
他刚你的那个那个，
我觉得这东西很抽象啊，为什么要这样？
给他出去。
就有人
我是摆美吧，我是做拿来摆美吧。
那我觉得这个直观多了。
我没有要他算什么，我只是要给他就
为什么你们数学家会发明这种又烦又没有用的东西？
就
没有，
很吓人呗，这个放那边，我感觉很美，
哪个
我觉得很美。
那我放到这个东西。他这放是几块肉？
就他要记录这个比赛，他要记录。刚刚讲还有什么 ？I 乘 J 等于 A。哦 ，I 乘 J 等于 A 吗？我记得 I L 等于 M，I 乘我讲乘 L。
没有，还要是拿这个。
对，M。
这个 L 跟 M 怎么扯啊？所以我说这个图有问题，不要这么跑。
他应该是有方法解的，他有方法解，应该不可能，他都给名字啊。
我也知道他有方法解，
他有方法解，
反正他不。
但是我没有想要比翻他。
但是我觉得这个图很反人类，所以我干脆放到不要的东西。
我觉得是有意义的，我没有拆分它吧。
它是8元数，8元数。
没有，
听过而已，就传说。
没有，那这个图，我说我没有想要比翻它，我是想在那边摆美嘛。
然后我觉得这个图，
他觉得不喜欢。
但是这个图，其实我觉得比这个图会更加难看懂。
那个哪一个？
大王这个表格是你很难眼睛酸。你看了你很好 reference 它，可是你不好理解它。
这有什么问题
啊？
这一个有一个 IJK 的，你 IJK 的地方，你看 IJK 的，你会比一个表格容易。在 IJ 等于跟 IJK 等于无，那么 IJ 就等于 Q，
他的意思是说，你虽然理解过好理解，但是要先理解先。但是他就说他还不理解。
对啊，你要有去理解。
对，
还有漂亮的。
对啊，我就是这样说，我是这个意思。我没有 define 啊，我没有 define 啊。好，我知道，那你可能以后找到这个就知道这个是什么。
我不觉得这玩意儿我们以后会学。
目前不，
因为它没有任何用。
比较少。
给100年都不会有人用的。
你要这玩意儿有用，那为什么你不再定一个16元数、32元数、64元数、128元数？
我跟你讲，
知道真的有，但是你放上去啊？
好像没有。
有，你100个都有。有，
但是应该最好用的是这3个。
我一点不觉得这玩意儿会有。
我记得他们讲，当你做变大的时候，就是可能说还有一些运算将会变得更问题。但是呢，一个在
从就是到4元数的升级交换率就4元数是没有交换率。
乘法还是加乘法是吗？加。
Hello. Yeah, should we ready? No. Hey. OK 啊，来收拾心情，最后1小时了。OK， 来，晚上还有来。workshop 什么 workshop？
Very interesting workshop.
Okay. 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 So we have that theorem, right? So it's time to define some terminology here. So we have the same setup as before. We have a group. Simply take any element, okay, and then you just look at the integer power of this element, and then this is a free subgroup to use now. Free subgroup. Okay, inside any group, just take integer power of this element. You will get a free subgroup. Okay, free one. Free one, huh? So what is this called? This is called the cyclic subgroup. Cyclic subgroup of G generated by X. Okay, so how do we denote it? We just put the angle bracket of X. Maybe you still cannot see the cycle, huh? How about if I reduce my set, I mean my group to a finite group, let's say Z6. So what can we consider here? Actually, right, we can consider the group generated by 2. But what is this? What's the all integer power of 2 here? So it is 2, 2, 4, 6, 8, 0, minus 2, minus 4, right? Okay, but what are these? These can reduce to what? These can reduce to just 0, 2, and 4. So it's you come back to 0, 2, 4, 0, 2, 4, 0, 2, 4, 0, 2, 4, 0, 2, 4. Okay, so you get a cycle. Okay, now does it make sense? For question? Tomorrow you 8. So 8 is equal to what? 2 to the what? 3. Do 3 times, right? So 2. So in this case here, we consider addition. So you need to ask every time what is the addition? What's the LLC? Correct or not? But this one is mod what? Mod 6 is what? 2 mod 6. So go back to 2 again. Does it make sense? So this one go back to 0 again. And so you get a cycle. Yeah. Okay, can see or not? If you cannot see, do more. 就是说讲讲如果你不是比人家聪明，你就要比人家努力，努力就可以胜出一点点。OK 吗？Because typically when people they are too clever, they won't work in the field they think they are excelled in. I give you an example. So when I studied in my department in ANU Australia, they are very good students. Graduate with first class, even their thesis got published. But do you think what happens to them or not? Do you think? Do you think? Do you know what happened to that person, a graduate? You might think, wow, he's so good, published, or maybe got PhD in maths. No, he didn't choose that pathway. He go do PhD in statistics. And maybe some of them go PhD in finance. You get what I mean or not? If you want to choose to stay in a field, it's not because you are good at it, because you love it. Only you can stay for long. 明白 ？OK， understand？ 因为很多学生会说，哇，这个课很难这个课很容易很容易我就去拿咯。It's not like that. We take courses, it's because we love it. It's not it is hard or easy. Even if it is hard, I still need to take it. That's it. 不管老师是谁，没有选老师，我们想要读就是去拿的。这样 Does it make sense? OK，当然你不要就不喜欢就不要拿了。但是我是说，如果你有心，你就拿吧，就不用怕拿，你一定可以过的。Yeah，好，Yeah，OK。有些老师讲哦，读 Pure Max 要靠天分哦，我讲不是，靠努力，就靠努力吧，没有天分这回事。OK 了，爱因斯坦都讲了，爱因斯坦讲嘛，爱因斯坦讲99%是靠努力，1%还是靠天分。哦，sorry，爱迪生讲。Anyway，someone next time we can share about a story of Edison. Edison also got a story one. We should talk about Edison. Yeah, 有算错没？哦，sorry，我算到那个 power 去了，说4次。对呀、2减2减2减2。对。sorry come back here. Here how we define this this power here this is the LOC, depend on LOC one. Okay, depend on LOC so don't confuse depend on LOC this notation does it make sense? Depend on LOC so you need to ask about LOC when you look at this power of an element. If LOC is plus here, that means you need to look at. So if this one equals to plus, then you need to look at plus. Okay, if multiplication, then you need to look for multiplication. Okay, now depend on this LOC here. This one LOC here. Okay. Question or not? Question? No? Okay, depend on your LOC. What is our LOC here? Our LOC is plus here. Okay, so how many times you add? 4 times. How many times you do LOC? 4 times. 4 times you do. Actually, only 3 times, correct or not? Just that you do it on 4 elements. 3 times, right? 1 time, 2 times, 3 times. 3 plus only, actually. But usually we just say we 4 times. So whenever we say, actually a bit ambiguous here, So, but not usually we just say that we do 4 times to say that we compose 4 things together. Okay, but you should really think that we only do it n minus 1 time. 1, 2, 3. Okay, but so this ambiguity you need to keep in mind. So actually you already observe some idea which we will call an order. Okay, an order of an element. So be careful. Last time we defined order on a group, but this time we define an order of an element. Okay, element and group you need to differentiate. So this is an element of a group. Okay, so what's this order here? This is a number. What number is this? This is the smallest, okay, positive integer. Okay, smallest positive integer such that what? Such that st s to the n equals to what? Okay, so let's try examples. I give you some example. Let's look at few groups that we know. For example, what group? For example, let's look at x2. Okay. S2, there's really one non-trivial element to look at, right? What's the non-trivial element here? How many elements in S2 do you know? 2. How do you calculate? How do you know there are only 2? How about I give you another question? How about Sn? What's the cardinality of Sn? What's the cardinality of Sn? Sn 2. N factorial, do you know how to calculate or not? This is the combinatorics you learn, the combination and permutation chapter you learned before. How to permute, how many ways to permute n elements. in the first place, you can put n elements, right? And then second place, you put n minus 1, and then so on. And then this build out the n factorial. Okay, so on. So here we have 2 factorial. So the non-trivial one is swapping 1 and 2. So you need to look for when these elements are return to identity. Okay, how many times you need to compose with yourself return to identity? Okay, how many times? You have 1, 2, right? You also have 1, 2, 1, 2, right? And then you have 1, 2, 1, 2, 1, 2, right? So you can keep doing. Okay, you can see that it periodically return to identity. Is it true? So 1, 2 is just 1, 2, but 1, 2 compose 1, 2 is identity. 1, 2, 1, 2, 1, 2 is what? 1, 2. And then 1, 2, 1, 2, 1, 2, 1, 2 is what? Identity again. So you can check that 1, 2 to the odd power will be identity. Sorry, even. Okay, even. So what's the order of 1, 2 in this case? So the order, so hence the order of 1, 2 is equals to 2. Why? Because 2 is the smallest positive integer among all the even integer, positive even integer. Okay, so it's the smallest one. You cannot say 4 because it already returned 2 when you take power 2. And so how about I give you some exercises and then you check. So let's do some exercise. So what exercise we can do? How about 2 in Z3 and then 1, 2, 3 in S3. Okay, let's try these 2 elements. Okay, try and check what's their order. Okay, I give you 2 minutes to work this out. What are their orders in their group? You need to find the smallest integer n such that after you take power, you return to identity. Try do this method here. You need to check when you get to identity, when multiply how n time with yourself. Multiply n time with yourself. See when you get back to identity. Okay. Right. So what should we do to 1, 2, 3 here? So we try and compose 1, 2, 3 with different power. Okay, let's do power 2. Okay, so if you do power 2, what do you get? What do you get? Still remember the calculation? 1 to 2, 2 to 3. Okay, so stop at 3. and start again from the right, 3 to 1, and then 1 to 2. Okay. And then 2 to 3, start again, 2 to 3, 3 to 1. So you can close it up. Okay, so this is power 2. Is this an identity or not? Not yet. Okay, so maybe we do again. So 3 times. So do 3 times, how to do? Do you want to calculate in the power of 3 or not? Huh? Or can you do something clever? Use associative. Use associative. So meaning what? We can first compute the first two first, which we already done, right? Which is 132. Okay. So this is the good thing about associativity. You no need to do product of 3. Then you can compute 2 by 2 first. So what's this? What's this composed to? 1 to 3, 3 to 1, close. 2 leh? 2 to 1, 1 to 2, again close. 3 leh? So until this stage, I think you should guess already, right? This should be an identity. There's last thing to go, because this has to be a bijection. Okay, 3 go where? 3 to 2, 2 to 3. So this is the identity. So you can see that all the positive integer power before 3 is non-zero. 3 is the first place to reach 0. So that means what? So that means that the order of the element 1, 2, 3 is 3. I add on question. If this order is 3, what's the inverse? What's the inverse? Can you see? If you have 1, 2, 3 to the power 3 is identity, what's the inverse here? What's the inverse of 1, 2, 3? Implies what? Who is the inverse? Can you split 1, 2, 3 to 1, 2, 3 to the power 2 times e? Is it clearer? What's the inverse here for 1, 2, 3? So it is just 1, 2, 3 to the power 2. Is the inverse of 1, 2, 3. But what's this 1, 2, 3 to the power 2? It is just 1, 3, 2. Okay. So from this equation, you can find who is the inverse for your element x. Okay or not? Yeah. So that's mean if your element has a finite order, that's mean you can get your inverse by what? By taking some power of your element. 你自己的 inverse 造出来了。If your order is finite, okay, you can build your own inverse. You make your inverse. Okay, how about the order of 2 in Z3? Have you computed? Not yet. Okay. So what do? Again, you look at integer power of your positive integer of your power of your 2. So what do? So again, what is the LC we consider here? We consider plus. Okay, we consider plus here. So 2 to the power 2 is what? 2 plus 2, which is 4, which is 1. 1 is what? Not 0 yet, right? Okay, because it's not the identity in addition. So what else we can do? We can continue do 2 to the power 3 is what in this case? How many times you add to 2? 3 times. So 1, 2, 3. You get 6. 6 is what? 0. 0 is the identity in plus. So meaning what? So we can conclude that the order of 2 is the order of 2 is 3. So what's the inverse of 2 here? 2 to the power 2, which is 2 plus 2, which is 4. Measures out, right? So 2 plus 4 is 6. Okay. So in this course, we will often introduce new language to cover all the phenomenon. Okay, all the phenomenon. We will use language to describe them. There are different ways to describe a same phenomenon. So you need to learn all these ways, okay, in this course. Because some way is preferable than the other. When we discuss different question, right, some language is better. Okay, so we will learn different language. So notation here. Now I will be using E identity 0, 1 as the identity element of my group. So depend on cases, I will use either one of them. So when do I use it? So let me tell you the general the type of cases I will use these element here. So E is the one for general or abstract group. I will use E. Okay. But identity, usually we reserve it for like function composition, identity function like that. Okay. And 0, we keep it for addition. Okay. So later, if the chapter 0 for our lecture now is out, 0 is the additive inverse. Additive identity. Okay. Additive identity for a group. Okay. With addition. And then 1, we'll always keep it for multiplication. Okay. Multiplicative identity. Multiplicative. Okay. Does it make sense? Okay. So usually when I write identity as 1, you think that, oh, that group should somehow multiply together. Some multiplication. If I use 0 for that group as an identity, then you should think of it. That LOC sum looks like addition. Okay. And then if I put identity, you'll think that, oh, this is not number already. Maybe it's a function or something else in this group. Okay. And then E is just all case we can use E. Okay. But we will be more specific if we have a more specific LOC later. Right. Okay. So in your mind, refresh, update already. Update your version. Update your version, your identity. So proposition. So let's do a proposition. If S has order n, okay, if we look back to our subgroup generated by this X here, what can we see? Actually, this set is only a finite set. Okay, I think we saw this example before. What's this finite set here? Can you imagine? If our X has order n, meaning what? X to the n already go back to identity. Okay, so how many elements inside this set here? Actually, it's a finite set. Okay, so what are the elements here? You could have identity, obviously, because S to the n is identity. And then you can do x squared, and all the way up to x to the minus 1. And then we claim, okay, we claim that these are only the elements inside this set. This set, x to the power n set. Okay, so we claim, we need to prove, we need to tell you why it reduced to this finite set here. So what's the cardinality of this set? Let's count. And if the cardinality of this set matches up with the number of the order. Okay, not matches up. There's a good reason for that. Okay, we'll see the proofs. All right, let's prove it. How should we prove it? How should we prove this thing? So you need to make a mathematical statement that you can prove. So how to make a mathematical statement you can prove? So what are you showing here really? What are you showing here? You are showing two set is the same. Okay, you are showing two set is the same. So what are the two sets that are the same? This is the integer power of x and also the set of n element here. So you need to show that these two sets is the same. Showing two sets is the same, how to show? If you want to prove set A equals set B, you need to show that A is a subset of B, B is a subset of A. Got in chapter 0 now, this thing. I don't know. You know, try check. This one is very important. A is a subset of B, B is a subset of A. No, that one is cardinality. Fourier Benzai is about cardinality. This one just showing two set is the same. Okay, equality of two set. Okay, so right. I think one is obvious, right? One way is obvious. Which way is obvious? Where is obvious? Which way is obvious? That is what. Can you don't learn what I write here? I want to do shorthand. I want to say that the left set is a subset of the right side, and then the right set is a subset of the left set. Can you not do this in your assignment? I just want to do shorthand now. Please write full in your assignment. Please don't learn this. I just want to do shorthand notation here. In the proper note, I will write properly, but now I want to save time. Hey, I change the direction, shouldn't change the position. Okay, so there are two things to show here. So which one is easier? What do you think? One place is obvious. One direction is obvious. Which direction? Try learn to see these. Whenever we want to show two direction, right? You should determine which one is easier. Second one is easier. Why? Sorry? 很多东西 not quite about 很多东西 but it's about how to check. Okay, second one, how to check. You just need to show that for every element in the right set is in the left set. But what are the elements inside there? All of them are in the form of x to the power z. Right or not? X to the power 0, x to the power 1, x to the power 2. So it satisfies the condition of left set. So surely all the elements in the right should be in the left. But now the problem is the other direction. The other direction, what happened? There are more things there. There are more things. What are the extra things? X to the negative power, and what else? X to the n. And any power that's greater than n. Not in the right set. So how? Close the book. So I sleep again. So how's that? 不知道. Use the assumption. What's the assumption says? Assume that the x has order what? N. So what happened to s to the power n in particular? Equals to what? Identity, no? Is identity on the right side or not? Got we settled one problem already. We settled one problem. How about x inverse 1? How about x to the n plus 1? So you need to settle all these elements, whether they are in this set or not. Okay. Okay, so let's do it. So I will write here, this implication is obvious. Okay, later we will fill it in. So now prove the other direction. Okay. Okay, so how many things we need to settle? We need to settle all the negative power. We also need to settle all the power that's greater or equal to n. Fair enough. For the middle one, is already on the right hand side. So we only need to settle those numbers. So two cases, right? So two cases. Let's start with for okay, so how should we put it? So since we know that since we know that 1 up to x to the n minus 1 is in the right set. Now we need to show that we need to show what? We need to show that we need to show that xm is also in the right set, or m not equals to, or for m, so for m less than 0, or for m greater or equals to n. Okay, so I need to settle all these cases. So let's think about how we settle these cases. Other than settling s to the power n equals to 1, do you know how to settle some other number? For example, x inverse, x to the minus 1. You know how to settle it? What does s to the minus 1 do? Okay, let's do some working here. Let's do working here. Whenever I teach, I like to communicate the idea instead of tell you how to prove. Because idea is more important than proving. Because proving can be different, but idea, you have to learn how to think. So in x inverse is what? Is the thing that you compose with x, you get what? Identity. But on the other hand, what did you know? There's only one assumption in this proposition. You cannot forget because there's really only one. What is that one? X to the n is also identity. So can you relate these two equations or not? Can you find inverse of x from this equation or not? What is it? X to the x minus 1. Okay or not? But we prove that inverse of a group is unique, right? Okay, so since what? This is working, this is just working. Don't write this in your assignment, write in your working. So since the group, the inverse, okay, the inverse of a group is unique, we should know that x inverse equals to x to the n minus 1. Okay, so we found who is x inverse already. Actually, it's in our set, x to the n minus 1. Okay, so you can try and infer what is x to the minus 2, minus 3, minus 4. They are all inverses of x2, x3, and then there should be line inside that group. Okay, so we need to prove it in general. So you need to start with easy example and then you prove it in general. Okay, so let's see, how should I bring this proof up for you? Can I follow what we did last time? What I did last time? Let me think. Okay, so like this. Let me do like this. So what do we do? So let's settle all the cases such that m, the absolute m is greater or equal to n. Okay, do you understand this or not? What's this? Let's write down so that we are on the same page. So these are all the integers such that m is greater or equal to n, or m is less than or equal to minus n. Okay, if you cannot imagine this inequality, what do you need to do? Okay, mathematics is real life. You need to draw it out. Okay, when you see this inequality, you have to draw. Draw what? Draw real line. Okay, so where is n? Let's say fix some n here, n and minus n. So where does n lie? N should lies in these spaces. Okay, less than or equal to n and greater than n. Why we split like this? You should note that our original assumption live in this interval from 0 to n here. Right or not? Okay. Okay. So why did I do this? So if you consider x to the power of m now, what happens here? I can simply reduce them to the region of x to the m mod n. Make sense? Because what? Because whenever you meet a multiple of n, it will reduce to 1. Or 0 in this case. 0 in this case is 0. Use the identity. Need example? Need example? Need example? Okay, need example. Like, again, Let's do some working here. When you see this kind of n, try and put some real n there. For example, what? N equals to 4 lah. Okay, let's look at this statement as n equals to 4. So here, what did you reduce to? 1x, x squared, and x3. Okay, look at some example. Okay, so in this proof here, let's say if we want to look at m greater or equals to 4, correct or not? What happened? What is x6, for example, in our case here? X6 is equal to what? X to the 2 times x to the 4. But you know that the order of this x is 4, meaning what? X2 will reduce to, sorry, x4 will reduce to the identity, which is, so that your x6 is x2. Okay, so is it mod 4 or not? Mod 4, right? Okay. So meaning I reduce all the cases that's larger than n and less than minus n to the region between minus n and n here. Okay, all the elements are reduced to the cases between minus n to n. So what left to settle? The only thing we need to settle is the negative integer interval here. Okay, so how do we deal with these? How do we deal with this? So now look at the point m from 0 to m minus 1. Okay, so in other words, I want to claim that all the element, all the negative power here actually is just inverses inside. Inverses for, I mean, obviously it's inverses for the positive intervals one, but I want to show that these inverse also can be written as some positive power here. How do we do this? Actually, this is a question on number theory. This is a question on number theory. Okay, so I again give you some working here again. So let me ask you first. This one is prelim. Let's think about what you learned before. What is minus 2 in mod, let's say, mod 3? What is minus 2 in mod 3? So following the logic we have in our class, minus 2 means what? Minus 2 means you add to 2, you get 0 mod 3. But what's the thing that you add to 2, you get 0 mod 3? Again, following the class in this logic, how many elements in Z3? Only 3 or don't have minus 2 actually. So minus 2 should be which one? Is 0, is 1, or is 2? 1, because there's only really one thing that you add to 2, you can get 0 in this. Match this what we learned in this class. Inverse is unique. Other element won't fit this inverse property one. Okay or not? So in general, how should we prove this? So in general, we see that the inverse of x to the minus m of xm, sorry, let's call it x to the m, is what? There's a formula for it actually. You can verify it, which is x to the n minus m. 哇，我不是从天上掉下来我也不是靠经验I prove to you. Okay, I prove to you. Since what? If you compose this n minus m to sm, what do you get? Do the same calculation we did just now. Expand it out. Cancel term by term. What do you get? You get if you do, let's say you do associative law. Okay, let's do associative law. What do you get here? X to the minus m plus m, which is what? Sn to the S0, which is what? Which is Sn times identity, which is what? Sn, which is, what is Sn? There's only one assumption you need to remember in this proposition, right? S has an order n. What does it mean? X to the n should be identity. Okay, it's the inverse of SM. Obviously, you need to check the other direction, but can you see that it's the same checking or not? Can you see or not? So remember, I want to remind you, go check another direction. So check whether xm times x to the n minus 1 is identical. Okay, check this. Yeah, I think we prove it. Yeah. So we reduce all the cases to this red region here. Okay. Does it make sense? Can or not? Understand or not? Because m is less than n minus 1, so n minus m should be inside the region. Okay, so let's last word here. Since 0 is less than equals to m, less than equal to m minus 1, then what? Then n minus m should be living in which region here? Living in, where is it? N and 1. Okay, so it's there in the right region we want. Correct one. Yeah. 0 actually we settle already. Don't care about 0 first. So we have a straight inequality. Okay? Yeah. Any question? So I will write out in full others proof, but did you get the idea or not? Okay, we need to reduce all the cases to the finite set here. Okay. Any question? Question? So if you want to say about experience, right, you need to go and compute this kind of cases. After experience, you need to explain why. Okay, you need to explain why it works. Okay, you cannot say experience work then work. It's different one because different people has different experience. Okay, so cannot generalize. Okay, cannot generalize. Okay, does it make sense? Yeah. Experience. Okay. After experience, you need to be logic. Okay. Thank you. See you tonight. Ah.